Hello, my name is Byron, and today I'm gonna present my final project. Okay, this project presents a ROS2 simulation and preliminary kinematic validation of a 6 degree of freedom aerial manipulator using the Archie robot. And the original proposal was based on a coordinated aerial swarm, but the world was recognized to first validate one representative robot, and this decision was important because replicating an unvalidated robot will only replicate its errors. In this video, the focus is the individual area manipulator. Okay, next slide. The first major decision was to reduce the project scope. Implementing several aerial manipulators at the same time will make debugging difficult because errors um, could come from the rubber geometry and the URDF files, the frame tree gazebo controllers, or the multi-robot coordinated logic. Therefore, the current project focus on one complete unit first, and the sworn idea remains as a future extension, but the individual rover must be defined, simulated, and measured before it can be replicated. The robot was implemented as a one connected kinematic tree. The word frame is connected to drum base link through a fixed Hoover joint, which represent the fixed Hoover assumptions. Then the drum base link is connected to the Archie base through arm mount joint. After that, and the active chain begins with joint 1 and ends at joint 6. The gripper is connected as a fixed tool, and this means that the active degrees of freedom remain 6 because only the 6 Archie joints are revolute and variable in the current kinematic model. The current kinematic model is a transformation change from the word frame to Lean 6. The drum post and the arm mountain transformation are constant, and because the drum is assumed to remain in fixed hover. The six variable transformation correspond to the six revolute joints of Archie. The final output is homogeneous transformation matrix that contains the position and orientation of link 6. At this stage, the model is based on URDF and TF, a fuel independent validation using a Denabit Hotted table, Python, MATLAB, or toolbooks, maybe. The implementation workflow starts with the Sacral and URDF robot description. The model is loaded in robot description, and robot state publisher use the joint states to publish the transformation function tree. The model was checked with check URDF, and the frame hierarchy was generated using view frames. The robot was then visualized in RBs, inserted into Gazebo, and tested with a Moveit interface. Moveit planning started working after correcting the joint's acceleration limits from 0 to a valid value. However, execution inside Gazebo still requires controller integration. And three joints configuration were recorded. For each one, the TF2 echo was used to obtain the pose of link 6 relative to where, and the measure position changed from one test to another. Pose 1 was approximately 0.298 and 1.035 meters. Pose 2 was approximately minimum 0.134, minimum 0.086, and 0.973. meters. Pose 3 was approximately minus 0.003, minus 0.140, and 0.877 meters. This confirms preliminary consequently different joints vectors produce different Cartesian poses. And the project was not fully completed as a final swarm system. However, a stable technical base was achieved. And the URDF and transformation function tree um, and was inserted and the model into Gazebo, measured three poses, and tested moving planning. The remaining work is clear, independent kinematic validation, Jacobian analysis, gazebo execution through controllers. The main conclusion is that the project shifted from an incomplete swarm and to a measurable individual aerial manipulator that can support future development. Thank you so much.